Swayam Prabha. Digital India. Educated India.
Namaskar. So, in the last class we discussed about superposition theorem and the source transformation. So, we will continue our discussion on various theorems with respect to AC analysis. So, in today's session we will discuss about Thevenin-Norton's theorem and the maximum power transfer theorem. So, let us see what are those theorems with respect to the AC circuit analysis. So, first we will discuss about the Thevenin and Norton's theorem. We will try to find out what would be the Norton's and Thevenin equivalents when we talk about the AC circuit analysis. So, in this case also the Thevenin's and Norton's theorems are applied in AC circuit in the same way as we did in case of DC circuit. Now, if you see, in case of superposition theorem we discussed that if there are sources with different frequencies, we need to create the separate circuits corresponding to each frequency domain and then process the information. So, in this case we will also create the different circuits for different frequencies and then finally we will use the superposition theorem to solve the circuit. Now, let us understand the Thevenin and Norton's theorem one particular frequency domain. We will first create the equivalent circuit. Equivalent circuit is nothing but Thevenin's or Norton's equivalent. So, how we will create Thevenin equivalent and Norton equivalents? We will use the same technique which we used in case of DC circuit analysis, where we will have one linear circuit. This linear circuit will be represented with the help of Thevenin equivalent, where we will have Thevenin voltage in series with Thevenin impedance. Similarly, in case of Norton's equivalent, a linear circuit will be converted into the Norton's equivalent, where current source, that is Norton's current source IN, will have the Norton's impedance in parallel. So, you can see that these two circuits, that is Thevenin's equivalent and Norton's equivalent, are dual of each other, and the Thevenin voltage, that is VTH, can be given as Zn, that is Norton's impedance multiplied by the current, that is Norton's current, and in both of the cases your Thevenin impedance and Norton's impedance will be same. So, in this way you can convert the Thevenin's equivalent into Norton's equivalent. Now, let us understand these particular equations with the help of few examples. First, we will use the Thevenin's theorem to find the Thevenin equivalent across the terminal AB of the circuit given in the example. So, here first we will find the value of ZTH. ZTH is nothing but the impedance seen from terminals A B while setting the voltage source equal to 0. Setting voltage source equal to 0 means the voltage source will be short circuited and current source will be open circuited. So, in this case we are having one voltage source. So, that voltage source will be short circuited, and when we will rearrange this particular circuit with the help of our knowledge on topological aspect of the circuit, we will come to know that this circuit will now contain two parallel combinations of 8 ohm resistance in parallel with minus j6 ohm impedance, and then the in series with the another parallel combination of 4 ohm and j12 ohm impedance. So, how our circuit will look like? The circuit will look like now as you can see in the figure. F and D are short circuited. So, they are clubbed together in this particular figure. So, if you go back to the circuit, F and D are now short circuited because you have put the voltage source as short circuit. Now, the updated circuit is as shown in the figure. Z1, that is the left leg of the circuit. Here 8 ohm and minus J6 ohm reactance are in parallel. So, when we solve it, we get the value of Z1 as 2.88 minus J 3.84 ohm. Similarly, for right side, J12 is in parallel with 4 ohm resistance. So, if you solve it, you get the value of Z2, and then finally, the equivalent impedance, that is ZTH, is nothing but Z1 plus Z2. So, now you have got Thevenin's equivalent of the circuit. Next task is to find out the Thevenin voltage. So, Thevenin voltage is nothing but the voltage across terminal A B. So, how to solve? We will first try to find out the currents I1 and I2. I1 is flowing in the DF segment, I2 is flowing in the right side of the segment. So, what is the value of I1? I1 you can say, because this voltage is connected across DF. So, you can write 120 angle 75 divided by 8 minus J6 will be the current flowing in the DF segment, that is I1. Similarly, I2 you can write as the voltage 120 angle 75 divided by 4 plus J12. Now, you have got I1 and I2. What you need to find out is VTH. So, how to find? You will apply KVL around the loop. Which is the loop? So, if you see, this would be the loop in which you will apply the KVL. So, if you start here, you will write VTH, then minus 4 I2. If you take the orientation like this rather than earlier assumption what we written. So, what we can write, this would be the loop and current direction we have assumed like this. So, in that case, what we can write? VTH minus 4 I2 plus J6 I1 equal to 0, and then if you solve, VTH will become 4 I2 plus J6 I1. Now, I1 I2 you have already calculated. When you place the values of I1 I2 and solve it, you get the value of VTH. So, now you have got the value of the Thevenin impedance, that is ZTH, and then you have found the value of VTH. So, you can simply draw the Thevenin equivalent. So, you will get VTH and in series with you will have ZTH, which you have calculated. Now, let us see another example where we need to find again the Thevenin equivalent for the circuit where you see the dependent current source. Now, to find the VTH, what we will do? We will find the value of voltage across terminal A B. So, how to find? If you see this particular figure, the value of current which is flowing through the current source is equal to I naught plus 0.5 I naught. So, if you apply KCL at this particular node, so what you can write? You can write 15 is equal to I naught plus 0.5 I naught. So, you get the value of I naught as 10 ampere. Now, you need to apply KVL to the loop on the right hand side. So, if you apply KVL, you can simply write, because the voltage across this current source is VTH. So, you can write simply minus, because the direction of current is opposite, to minus I naught 2 minus J4 plus 0.5 I naught into 4 plus J3 plus VTH equal to 0. So, when you solve, you get the value of VTH as minus J55, or you can write VTH as equal to 55 angle minus 90 degree volt. Now, you have got VTH. Next task is you need to find ZTH. So, to find the ZTH, we remove the independent source. So, independent source in this case is the current source. So, if you remove the current source, the updated circuit will be like shown in the figure, and now across terminal A B we apply a current source having value 3 ampere. So, we have taken 3 ampere as an arbitrary choice, you can assume any value. The Thevenin impedance ZTH will be equal to Vs upon Is. So, what we have to find out, first we have to find out the value of Vs and then we will divide Vs by Is. So, if you apply KCL at the node, what you get here, your Is, that is 3 ampere equal to I naught plus 0.5 I naught. So, what you can write simply, the value of I naught equal to 2 ampere. Now, let us apply KVL to the loop on the right hand side, that is the loop which you see here. So, you apply KVL. So, what you can write, Vs is nothing but the current I naught is flowing in both of the impedances. So, we can write I naught into 4 plus J3 plus 2 minus J4. So, it will be equal to Vs. So, when you solve by putting the value of I naught, you get Vs as 2 into 6 minus J. So, now you have Vs available, ZTH can be simply written as Vs upon Is and you get the value of ZTH. So, now you have got VTH as well as ZTH, we can create the Thevenin equivalent. Now, in this particular example, we need to find out the value of I naught, that is the current flowing through the segment AB using Norton's theorem. So, to find out the Norton's equivalent, first we will remove the load from terminal AB. Now, what we need to find out? We need to find out the value of Norton's equivalent impedance, that is Zn. So, when you are asked to find the value of Zn, first what you will do? You will short circuit the voltage source and open circuit the current source. So, you will get the updated circuit as shown in this figure. Now, if you see this particular segment, that is 8 ohm resistance in series with minus J2 ohm reactance offered by capacitance, and then 10 ohm resistance and J4 reactance offered by the inductor. So, this will be shorted because you have a current voltage source connected and which was short circuited. So, this particular leg will be completely short circuited. Then in that case the Zn will be left with only 5 ohm resistance. So, what you can say, your Norton's equivalent impedance is 5 ohm. Next task is you need to find out the value of In. To find the value of In, we short circuit the terminals A, B and then we solve for the value of In. Now, from this figure you can see that the current source which is there in the figure is coming between two loops. So, what you can create? You can create a super mesh because current source is common to both of the meshes. So, we will create one super mesh containing mesh 2 and 3 and then we will write the mesh equation. So, for mesh 1, what you can write? Minus J40 plus the value of the impedance, that is 18 plus J2 into I1 minus I2 into 8 minus J2 because I1 I2 are in opposite direction here. Similarly, minus I3 into 10 plus J4 because I1 and I3 are also in opposite direction here. Now, for the super mesh, what you can write? Minus I1 into 18 plus J2 for this segment because here I1 is in opposite direction of I3 as well as I2. So, you can write minus I1 18 plus J2, then plus I2 into 13 minus J2 because 8 plus 5 will become 13, 13 minus J2 plus I3 into 10 plus J4. So, you got the mesh equation for super mesh. Now, if you see node A, at this particular node the value of, you apply KCL at this particular node. So, you can say that the value of I3 equal to I2 plus the value of current source, that is 3. So, I3 will become now I2 plus 3. Now, if you add first two equation, you get the value of I2, that is J8, and then you can put the value of I2 in this equation, you get I3 is equal to 3 plus J8. Now, what is I3? I3 is nothing but Norton's current. So, that is IN. So, you got now the Norton's equivalent. So, how you can write? You can write Norton's equivalent current, that is 3 plus J8. In parallel with, you have Norton's equivalent impedance, that is 5, and then you connect now the load across AB, that is 20 plus J15. Now, you can find the value of I naught with the help of current division. So, you can say I naught is nothing but 5 divided by 5 plus 20 plus J15 into IN. IN is 3 plus J8. So, when you simplify, you get the value of current I naught. Now, let us come to the another theorem called maximum power transfer theorem. So, in case of DC circuit, we solve the problem of maximizing the power delivered by a power supplying network to a load RL. So, how we solved? We solved mathematically and saw that the first the circuit is represented by its Thevenin equivalent, and then mathematically we proved that maximum power would be delivered to the load if load resistance is equal to Thevenin resistance. So, this is what we proved in case of DC circuit. Now, the same concept we will extend for the AC circuit, and we will try to find out the condition under which the maximum power would be transferred to the load if AC source are connected to the circuit. So, now again let us consider the circuit. We consider a linear circuit where a load ZL is connected. So, this linear circuit will first convert into Thevenin equivalent. So, we will have VTH in series with ZTH, and then load ZL will be connected across the Thevenin equivalent terminal. Now, the load is generally represented by an impedance. So, that is why here we are representing load with ZL. Now, let us represent ZL and ZTH in rectangular form. So, what you can write? You can write ZTH is nothing but, that is RTH plus JXTH. So, ZL you can write as RL plus JXL. So, basically this is nothing but RTH plus JXTH, and ZL is equal to RL plus JXL. So, now ZTH and ZL you can divide into the resistance and the reactance component. Now, next is you need to find out the current which is flowing through the load. So, what is the value of current? Current is nothing but VTH divided by ZTH plus ZL. So, that is ZTH plus ZL. Now, you simply replace the values with the rectangular form of the ZTH and ZL. So, you can write simply RTH plus JXTH plus RL plus JXL. So, now you got the value of I. What is the average power delivered to the load? The average power delivered to the load can be written as P is equal to 1 by 2 I square R. Why 1 by 2 term is coming? Because this is not the RMS value. So, if it is a peak value, you will get the value P as 1 by 2 I square R. So, if I is RMS, then you can write I RMS square into R, that is the value of average power delivered to the load. So, here in this case P will be 1 by 2 I square R, that means VTH square into RL by 2. So, here R means RL, the power delivered to the load, and then we write the value of I in terms of VTH and the ZTH and ZL. So, we can write power P in terms of VTH, RL and RTH like shown in the slide. Now, what is the next task? Our objective is to adjust the load parameter, that is RL and XL, so that the value of P is maximum. So, how to get the value of maximum P? To do this, we set del P by del RL and del P by del XL equal to 0. So, if you obtain the value of del P by del RL and del P by del XL using this equation, what you can write? Del P by del XL is nothing but VTH square into RL into XTH plus XL divided by RTH plus RL square plus XTH plus XL square whole square. So, this is what you get when you differentiate this equation with respect to XL. Similarly, when you differentiate power P with respect to RL, you get the expression as shown in the slide. Now, if you when you set del P by del XL equal to 0, what will happen? So, this cannot be 0, this is again cannot be 0. So, what can be 0 is XTH plus XL. So, when you set XTH plus XL equal to 0, you get the condition that XL should be equal to minus of XTH. Similarly, when you set del P by del RL equal to 0 and solve this particular the part of the expression, you get RL equal to under root of RTH square plus XTH plus XL square. Now, if you put the value of XL is equal to minus XTH in this expression, you can simplify it and you get RL is equal to RTH. So, now for maximum power transfer condition, you got two expression for the condition, that is XL should be equal to minus of XTH and RL should be equal to RTH. So, what you can write now, that for maximum average power transfer, ZL should be selected in such a way that XL should be equal to minus XTH and RL should be equal to RTH, or you can write ZL is equal to RL plus JXL is equal to RTH minus JXTH. What is this? This is nothing but the complex conjugate of ZTH. So, you can easily say that ZL is equal to complex conjugate of the Thevenin impedance. So, now what would be the maximum power to be transferred? In this case, P max, the maximum power which would be transferred would be equal to VTH square by 8 into RTH. How you got? You just simply put the value of RL as RTH and XL is equal to minus XTH. So, this will be anyway become 0. This will be equal to 4 RTH square, and then in numerator you will get VTH square into RTH by 2. So, 1 RTH will be cancelled out and finally, you get VTH square divided by 4 into 2, that is 8 RTH. So, this is what you get under the maximum power transfer condition. So, if you compare from the DC circuit, this is slightly different because of the introduction of reactive component in the impedance. Now, in case of AC, if your load is purely real, what would be the condition? the condition for maximum power transfer will be obtained by setting XL is equal to 0. So, where you will put the value? You set the value of XL equal to 0 here. What you get? RL would be equal to under root of RTH square plus XTH square. So, in case of DC, the maximum power transfer was obtained by setting RL is equal to RTH, but in case of AC, the value of RL would be equal to under root of RTH square plus XTH square. So, what does it mean? That means that the maximum power transfer to a purely resistive load, the load impedance, that is resistance in this case, will be equal to magnitude of the Thevenin impedance. So, now we will use the maximum power transfer concept to determine the load impedance ZL that maximizes the average power drawn from the circuit. Now, if you see the circuit, you will have 10 angle 0 as a voltage applied, and then resistance 4 ohm in series with the voltage source. In parallel, you have 8 ohm in series with minus J 6 ohm as a reactance offered by this capacitor, and then J 5 ohm reactance offered by the inductor. Now, the load ZL is connected across the terminal. So, first task what you have to do is that first you need to obtain the Thevenin equivalent at the load terminals. So, first we will remove the load from the circuit. So, when you remove, you get the circuit like this, where you have 10 volt, 4 ohm, 8 ohm and the minus J 6 and J 5 ohm connected. So, you will get the circuit like this. To find out the Thevenin impedance, you will short circuit this. So, your circuit will become like this, and this 4 ohm resistance will now be in parallel with 8 ohm resistance in series with minus J 6 ohm reactance. So, if you solve this, the parallel combination of this, and then the result is added with J 5 ohm reactance offered by the inductance, you will get ZTH as 2.933 plus J 4.467 ohm. So, by solving this, you get the value of ZTH. Now, you need to find out the value of VTH. So, how you will be able to find out VTH? This is a simple circuit where you can utilize the voltage division concept and find out the value of VTH. So, VTH will be nothing but 8 plus minus J 6 divided by 8 minus J 6 plus 4 into 10. So, when you solve, you get VTH as 7.454 angle minus 10.3 degree volt. Now, you got VTH and ZTH. Next task is you need to find out the value of ZL, which is the load connected across the terminal of the Thevenin equivalent. So, what will be the value of ZL for maximum power transfer? ZL will be equal to complex conjugate of ZTH. So, what will be the value of ZL? ZL you can simply find out by taking the complex conjugate of ZTH, that is 2.933 minus J 4.467 ohm. So, this you can see that the load impedance you can easily find out by creating the Thevenin equivalent. So, with this we can close our today's session. In this session we discussed about the maximum power transfer theorem, Norton's and Thevenin's theorem with respect to our AC circuit analysis. So, in the next lecture we will discuss about the magnetically coupled circuits. Thank you.